All right, we'll get started. So welcome everyone to the first 2026 Action Team webinar series leading up to our main conference events on June 9th through the 11th. And you can see the link in the chat for more details on the registration. Late pricing will begin on May 12th, so we encourage you to register before that. My name is Bonnie Whitney. I am a computational materials engineer from Solvus Global. Today we have HAMR presenting on cold spray AM. Where does it fit? We encourage Q&A throughout today's session, and please use the Zoom feature on the bottom of your screen to submit your question. The recording of this webinar will be available online afterwards. So Mike is the CEO of HAMR, and I will let him introduce himself and get started.
Great, thank you, Bonnie. So hi, everyone. Today, as Bonnie mentioned, I'll be talking about cold spray AM and where does it fit. Started out with my camera on so everyone can see a smiley, friendly face. I'll probably turn it off for the presentation just so we can focus on the content. But yeah, what I would like to look at and focus on today is where does cold spray fit within sort of the broader manufacturing ecosystem, and then specifically within the additive ecosystem. So we believe kind of every tool has a role to play and has a use case. So this talk centers around what is that use case for cold spray additive. So with that said, we'll get started. We'll also point out, because it's kind of funny, we use AI generation for a couple of images throughout here. So on the first image, you see the puzzle piece doesn't fit. It's kind of in line with what we're talking about. Where does cold spray fit? Does it fit? And then, how can we make it fit? So where is it best used within your manufacturing strategy? To put this presentation into context, I think it's kind of helpful to describe our team and what we do. This isn't going to be a pitch for HAMR by any means. It's just a sense of why we care and why it's important to us. So at our company, we develop advanced materials and manufacturing for components that function in harsh and extreme environments. So that's things like directed energy, munitions, metasurfaces for communication, high power communication, hypersonics, undersea propulsion. So all these different applications that require sort of advanced materials or advanced manufacturing solutions. And then on the other side of the house, we take those manufacturing capabilities we take the expertise that we have in this team that we've assembled, and we leverage those for the domestic industrial base. So using our capabilities to be contract manufacturers, supporting expeditionary, sustainment, and production. And we do this at Neighborhood 91. So Neighborhood 91 is a sort of consolidated commercial advanced manufacturing campus in Pittsburgh, Pennsylvania, right near the airport. And what's sort of unique about it is the Pittsburgh region itself has a lot of historical and legacy manufacturing capacity, tool and die shops, powder generation, materials generation, but taking that and sort of consolidating it not just regionally, but also locally onto a single campus. So we as contract manufacturers and R&D service providers can leverage upstream facilities and utilities, and then downstream post-processing and Q&A, and focus on what we want to do, which is the manufacturing side of things. And while we focus on what we want to do, it's understanding what tool works best for the application at hand. So at HAMR, why we really care about the question of where does cold spray fit, we work backwards from the problem and select the right material and process to address that problem. So we work in a relatively well-defined material space of materials for harsh and extreme environments and materials for sustainment. And we look at those problems, we look at those challenges, and we say, what is the material that would best support this, and what is the best way to manufacture that component and that material together? So for us, we're not a cold spray shop. We have multiple styles of additive and advanced manufacturing capabilities in-house, and then by being on the Neighborhood 91 campus and within that regional ecosystem, we have access to really every single modality that's out there. So we want to work backwards from the challenge, select the right manufacturing technology, and utilize that to provide a solution. So we need to know, where does every single piece of technology fit within the broader ecosystem? So to start answering that question, this is a bit of an eye chart. So admittedly, there's a lot of numbers on here, but the focal point is that you can range from low to high for sort of every variable that we might think about. If we look at wall thicknesses, we can have sub-millimeter, few hundred or less than 100 micron wall thicknesses for powder bed fusion. And then we can go up to cold spray and wire arc DED, where our minimum wall thickness or feature size might be somewhere in the realm of 5 to 10 millimeters. Likewise, build rates. We can have build rates that are as low as tens or 100 cc's per hour, or a few hundred grams per hour, and we can have build rates that are as high as several kg to tens of kg per hour, for some of the solid state methods and the wire based methods. Likewise, part dimensions. So cold spray fits within this. It tends to favor the high build rates, the large part sizes. It doesn't have a lot of resolution. So it's in a space that's somewhere close to like a laser wire or a wire arc DED. And then the system cost also kind of fits similarly in that space, a little bit less than the really large powder bed fusion systems or e-beam systems, more comparable to something like a typical wire arc cell. And then we can start to dive into the economics, which we'll really do on the later slides, but we can look at the cost of operating a system. So if we sort of normalize what's the amortization cost of a machine, with a few assumptions at the bottom, and then divide that by how much metal can it make an hour. So instead of trying to worry about the part and part complexity, just a rough estimate of, hey, you can make X amount of metal an hour, you can operate this many hours a year. How much material can you pump out on these systems, and what's the cost then per kg of a part, to get kind of a rough estimate. And this is where we can start to see cold spray really shine. So that's going to be the first half of today's talk. Where does it fit? What are the things it's good at? What kind of properties does it have? What are the economics? What are the challenges? Where do we need more development? Where do we need more research? Where does it sort of fall short? And then the second half of the talk is going to be about more of novel applications. So not only does cold spray have a role, we believe, in that additive tool belt, but we also believe that it's not only a specific tool, but a unique tool. And it can do a lot of other things that are either challenging or maybe not even possible with some of the other additive modalities. So when we look at the types of materials that it can process, when we look at doing things with refractories, with cermets and composites, and unique ways of operating, like cladding, 3D grading, functionally grading, hybrid AM, and expeditionary, that's when we see cold spray starts to really shine. And the only other modality that's really comparable to it is potentially powder DED, in terms of having this really large degree of flexibility. So kind of drilling down into it more, where does it fit? So consolidating that eye chart into a digestible table here. Feature size, we're looking at parts that have minimum feature sizes, ideally greater than 6 millimeters, to reduce the amount of machining that we need to do. Component sizes, it can do any component size, but where our bang for the buck is when we start to get to intermediate to large and even extra large components. The material is flexible. This is an advantage. We'll talk about this throughout the discussion today, but the materials that cold spray can do are traditional manufacturing alloys. So we don't have to do a material swap. So when we look at qualification and the challenges that are there, having a material swap and a process swap can sometimes be doubling your difficulty. And it's also amenable to sort of non-standard materials. And then the requirements for those materials are also flexible. So in terms of particle size, morphology, shape, in cold spray, we in fact sometimes like a powder that is not spherical. So water atomized, more economical powders. We've utilized mechanical powders. Our neighbors, Metal Powder Works, and they generate an angular powder, and we've used that to good success. So the material requirements are flexible. The timeline is fast, and timeline there is timeline for from time you get the part in till time you can print. It's easy to slice. We can go from CAD to part very quickly, and we can print very quickly in cold spray additive. And I say we here, this is really royal we. This is users of this technology. So it's not that challenging to kind of get your hands on this, get your head wrapped around it, and get printing. And then change out time is also fast. So typically when we talk about AM, we talk about sort of high mix, low volume. Whether that's necessary or accurate is something we'll touch on here in a minute, but the change out for cold spray is fast. It's a change of a powder feeder or a clean of a powder feeder. So in a production environment, the change out of a powder feeder could be minutes. So it's a fast change out, which means that we can be a very responsive type of modality. So we start looking at the applications. Where do all those benefits sit? Short lead alternate for forgings and castings is kind of one of the first ones that we've really focused on. So some examples there would be aluminum alloys and maritime alloys, and that's where we found some first success and where I think the broader community has in looking at larger parts. So the larger the part, kind of the higher the value proposition. And for the 6061, 7075, and those materials, it's helpful because we can process these traditional alloys. So again, we don't have to use reactive. We're not using RAM powders. We're using traditional 6061 aluminum, 7075 aluminum. So the ability to produce those materials with cold spray is advantageous. The DIB, MIB, SIB, whatever you want to call it, the industrial base sustainment. So in this case, again, being amenable to those traditional materials is helpful because we can provide those components. And it's also goes to the responsive manufacturing. So with cold spray being inherently able to kind of swap over to new materials and to go from CAD to part very quickly with the slicing methodology developed by Speed, that allows us to have a very responsive manufacturing strategy, or allows the community to do so. Expeditionary, cold spray does not require argon, and it doesn't require helium either. So the vast majority of what we print currently is with air. We can use nitrogen, but we tend to go for air anytime we can to maintain economics. So from an expeditionary perspective, cold spray has that advantage of we don't need those logistically challenging process gases. And it's largely a mechanical and pneumatic system. So why I bring that up is we don't have an optical chain. We don't have a lot of digital controls that we have to worry about. It is by and large a mechanical system. It's got high pressure piping, high pressure tubing, but these are all things that a lot of people might be familiar with in an expeditionary environment or at depots or at forward operations. So it's a technique that really lends itself to being expeditionary. And then there's significant potential in the advanced material space. So it can process some really novel materials and clads, composites, gradients, and we'll get into this later in the talk. So from the sense of where it fits, we can start to see, but the question that's kind of first on a lot of people's mind is, what are the economics in the process? So can you actually make a part that we can buy? Typically, when we talk additive, the first part of the conversation is, well, you're going to pay for it. Um, and a lot of that comes from being first sent around powder bed fusion. We like powder bed fusion, we use it, but in some ways, it's sort of challenged the AM community, because then the focus was always complexity is free, and additives only good for complex parts, not for castings or boring parts. It has to be really complex to make sense, and we're not worried about how long it takes. We're just worried about the complexity of the part, and that's because those kind of initial machines and development in the community were slow to process. They were hard to process. They were expensive, and you weren't able to make an economical part. That's not really true. So that's what I want to show here, especially for cold spray. So this is sort of broad strokes example that we've done. This is a part that we've similar to something that we've quoted out. So just a conical geometry somewhere in the 2 to 3 feet range in terms of length, and looking at what's a sort of first article cost, and then what goes into that cost, and then moving into LRIP and production type of costs. And we see that for a first article, these costs are all unloaded, so just kind of raw costs for the part, and then whatever your operating or facilities costs would be. And we see that there's NRE like every other process. And the first article maybe landed at around 30K for a 2-foot long part, comparable to a relatively moderate sized forging. This would be for aluminum 6061. And then when we move into LRIP, we see that equipment utilization, post processing, still larger chunks. Labor is relatively small though, and we see that sort of consistently throughout. The labor is not the driver of the cost, and really the equipment utilization isn't the driver of the cost for the lower rate productions. And when we move to high rate production, at this point we have a lot of assumptions. We're happy to talk through those with people. But we've now internalized our machining. So we're not sending it out to a job shop that we quoted. We're doing all the machining in-house on our own CNCs. We have machine operators. We're assuming that there's QC and QA operating in-house, heat treatment, again, in-house. So we're not sending these out to job shops. So the post-processing starts to effectively be eliminated and absorbed into just a facilities. And now we see that the largest chunk is just the equipment amortization and the materials and consumables, and we've dropped our price down to about 10K per completed part. And that is a extremely competitive price for a forging of this size, especially with the lead time and production capacities that we can hit. So the answer to can it be economic is yes. It's a fast process. It scales well. First articles to LRIP can usually be done on one machine, because one machine can process quickly, and that also gives the user the ability to scale up in a useful and sustainable manner. So kind of continuing to look at the costs, rather than reinvent the wheel here, we borrowed this from Barnes Global Advisors. They have designing for AM workbook through some of their AM workshops. And this one looks at cost comparison by AM method. So it gives a sense of normalized cost and what goes into the major costs for each modality. So when we look at cold spray AM, we see that the printing itself is really not the major cost driver. It's the feedstock, and we would agree with that. The feedstock really starts to be kind of the major driver. And then especially at low rate, post-processing is one of the bigger costs. We're near net shape, but we're not fine featured. So this is the drawback. We can make things quickly, but we do have to machine them. So we're going to print in a green state, we're going to heat treat, and then we're going to machine. So the fact that we heat treat and machine each part certainly adds cost. So this can make it sort of challenging for those prototypes and that LRIP. But once those costs are internalized, or once we productize and we have a single setup and we're just chewing through that setup on the machining side or on the heat treat side, that brings those post-process costs down dramatically, and then the process can really shine in terms of the economics. The other kind of first thing that people generally care about when they're looking at a new modality or a technology is what can you make with it. So okay, we can economically spray some metal. What does that metal do? What are the properties? So I have a plot here of a couple different material systems. This is by no means exhaustive. This takes data from colleagues at Speed, as well as Powders on Demand, and then material that we've printed. I'm certain that there's others out here who could add on to this, but this is kind of a good starter of what's in the art of possible. And the takeaways I want to highlight on the right. So first off, there's really been minimal funding in this technology to date. So relative to the other additive modalities, not only has cold spray been around for a much shorter time, but there's been tens of millions of dollars that have been dedicated to powder bed fusion and to wire arc and to the other modalities. Cold spray, that is not at all the case. And yet with a few million, I think among the entire cold spray community, there's already a number of materials that are meeting and exceeding the casting and forging standards, some of them developed on IRAD by companies. So I think that's a really encouraging spot for the process to be in. So you'll see 6061 on the left. Cold spray additive can meet and exceed AMS 4127. So we are able to meet and exceed forging level properties of 6061 with cold spray additive. Likewise, on the maritime side, NAB and copper nickel, there's going to be a lot more information that'll be public by the time of CSAT that Penn State's going to present on. But for what's been done privately, there's already evidence of meeting and exceeding the NAB and the copper nickel ASTM standards in cold spray additive. And then when we look at some of them, maybe higher strength materials, more challenging materials, we see cold spray starts to struggle a little bit, tends to have good strength, and then we tend to have a little bit lower elongation. But again, I'll note a lot of this goes back to development. So these are some of the least developed materials, and we already have good strength out of these materials, and it's just working on getting Z strength up. So 316, for example, that's 29 versus 30% elongation. So, or 27 versus 30% elongation. So pretty close to what we're trying to get with the MIL PRF standard in cold spray with effectively zero development. 17.4, really high strength material that Pod's been able to make, and then CP tie also looks pretty good. So there are some caveats. Harder materials, tougher materials are more challenging. That's definitely not the strength of cold spray. So if you want a really high strength steel, cold spray may not be your best bet, or at least looking at it for a more traditional approach. But properties, we can make them. It's economic. So why is it not proliferated? What are the challenges, right? So we don't want to come across as if that, this is the best thing since sliced bread. Everything is rainbows and butterflies. There are certainly challenges. A lot of them mimic what we see in the other AM modalities. The first one, I think, to highlight, the simplest one is just build efficiency. So there's a fun little AI image that sort of approximates the cold spray splat phenomena. So as the particle comes in, impacts the surface, splats, deforms, we make our part. If our material is too hard, too high strength, too brittle, it can come in, it can break, shatter, or it can come in and it can rebound. And that leads to a low deposition efficiency. At the best case, at worst case, we just get no buildup. So if we have a low deposition efficiency, if most of our material gets bounced off or breaks, that means that it's a very expensive process now. Unlike powder bed fusion and some of the other modalities, we're not able to reuse our powder at this stage. So whatever we lose is lost forever. And there's a few ways to think about this and a few ways to kind of assess what the likelihood or strengths of what you're going to do are. So we see that there's something called a critical velocity in cold spray, and that's basically a velocity where we go from the reflection on the right to the splat on the left. And we see that that is a function of the material properties. We see that that varies by alloy system, and we have to achieve some velocity in the particle. And that velocity is dictated by the temperature, pressure of the gas, density of the particle, and so forth. And then within an alloy system, there we see that as we increase the strength of the alloy, so going in the right here from pure aluminum to aluminum 7075, that increases the V crit or the V crit ratio. So how fast do we need to get the particles? So ultimately, we can relate that. It's arguable in the literature, but to something like the spall strength of the material and the bulk sound velocity is one approach. The takeaway, though, is that these higher efficiency materials tend to be commercially pure metals. They have relatively achievable critical velocities. So and then a lot of aluminum alloys and a lot of copper alloys. So generally speaking, softer alloys. Lower efficiency materials where we're thinking less than 40% DE. These are really high strain hardening alloys. You can imagine as that particle tries to deform, it's going to be a challenge. High strength alloys, brittle alloys, so things that are brittle at low temperature. Cold spray is not a very high temperature process. The particles don't stay that warm for that long. And high temperature alloy or high entropy alloys, excuse me, tend to have very high spall strengths, so tend to be a little more challenging to deposit. The next issue that can challenge cold spray is clogging. So we have different examples of clogging here. You can have clogging in a barrel, clogging in an injector, clogging in your powder feeder funnel, clogging in your nozzle. There's metal powder flowing. There's a high probability that there's somewhere it can clog. And since we are primarily pneumatically driven, that is kind of the biggest sort of in situ process challenge that we face in cold spray. To try to liken this to something in the other AM modalities is kind of like a recoder failure. Everything can be going great, and then you have a recoder failure, or wire pull away or slumping. So you have to, when that happens, you have to go back, double check, was everything done correctly? Are our supports generated correctly? Are our feeds and speeds correct? In the case of cold spray, often comes back to the powder. Is the powder correct? Was the powder handled correctly? Do we have the right particle size, the right moisture content, etc.? The cause, this is some work that's been done by Penn State and Tony Nacarelli. It's been linked to a combination of particle size and impact angle, where we can see certain particle sizes and impact angles tend to clog. And fortunately, there's a couple solutions. So one that's been more and more broadly adopted is the cooled nozzle. So either using air cooling or some sort of fluid cooling for the nozzle, which tends to help from mitigating that particle adhesion in the nozzle and building up clogs. There's also utilization of ceramic materials. So moving from metals and PBI and cermets to full ceramic materials. So silicon carbide and silicon nitride, things that are covalently bonded that don't want to stick to metal. So you can think of it as, can we deposit on it? If the answer is no, generally speaking, then that probably makes a good barrel material. And the last way that the community's been looking at solving this, and maybe the most novel ways, is changing our nozzle design. So if you're familiar with rockets and space, aerospike nozzles are kind of a novel approach that a lot of people have been trying to get to work. And we can take that in cold spray, and what it allows us to do is inject our powder past the throat of the nozzle and into a region where the fluids a little bit cooler, and also more importantly, into a region where it's not likely to impact anything because it's past the diverging section or past any wall that it can impact. So there are solutions. It's a problem. It's ongoing. It's something that's monitored, and it's just something that needs to be designed around. Another challenge in cold spray is delamination. I have a couple examples here. We can delaminate from our substrate when we're operating cold spray as kind of a coating approach, and we can delaminate from our build plate. You see an unfortunate delamination here of a relatively large part. So that's both surprising and scary when it happens. And fortunately for this, we can borrow from kind of what's known, what's been done in the literature. So there's analogous failure modes. In additive, there's support failure, there's failure from the build plate, and there's a lot of solutions that have been simulated, modeled, and designed. Likewise, for coating delamination, this is kind of a chief concern in the thermal spray world. So if we look at thermal barrier coatings, that is the primary function is how do you avoid delamination in a system that is prone to delamination. So a lot of these challenges have been worked on previous to cold spray. It's not new, so we can borrow some of those solutions. So in the case of the top, we can look at something like a raft or a skirt, borrow from what we do on our FDM benchtop printers, and it works. It's certainly a viable approach, and we can change our DFAM, reduce our stress risers, look at our contact area, contact patches, and use that to ensure that we have adhesion. And then from the coating side, a lot of it comes down to thermal input and managing thermal expansion and mismatch stresses. And you can see from the left to the right that we're able to get these coatings to adhere. So fundamentally, much of this comes down to management of heat input, stiffness, and residual stress, similar to what we do elsewhere. It's a similar challenge that we have to face in cold spray. And it's a good segue to overall residual stress management. So again, every additive, every manufacturing modality has to manage residual stresses. There's stress risers and thick to thin transitions. It's a challenge in castings, forgings, it's a challenge in additive. So on the right here, we've shown that we can make large parts. We can do it repeatedly and reliably. So those are 6 3/4 diameter on the bottom, several feet long, and then you see the top. That's in the realm of around 13 inches and are about 1.5 feet or 2 feet. And then the part that Jake is always the person who ends up taking the pictures. Jake's holding a part that's between 20 and 24 inches. So it can make large parts, and we can do that successfully, and we can manage the stresses. But there are times when we don't manage the stresses or when parts fail. So cracking is a challenge in cold spray, just like it's a challenge in the other modalities. And it's something that we have to address and something that we're working on. And ultimately, we want to take it from the left to the right. So move from geometries that tend to have cracking and setups that tend to have cracking to setups that don't. And we know that we can because we've done it. And how is on this next slide. And this is where I think there's a lot of focus from the community and a lot of room for work is assessing, modifying, and accommodating the residual stress in cold spray. So there's sort of 4 knobs that I think we can turn. There's green body strength, DFAM designed for AM, there's feedstock optimization and thermal management. So from the green body strength perspective, I mentioned earlier in CSAM, it's ideal to spray with air because when you spray with air, you have the most economical process. The downside of spraying with air is unlike spraying with helium at really high pressures and temperatures and getting something that's ductile off the bat, we have something that's brittle. There's effectively no elongation. So if the stress exceeds whatever the UTS is of your green body, you will have cracking. So what can we do to modify the green body strength? Turning that knob. So that's changing process variables, also relates to feedstock. So getting the optimal feedstock for the process to maximize your ductility and strength in the green body while minimizing your need to go to really aggressive energies is an area of effort that we've focused heavily. DFAM, similar to all the other other processes. So looking at our radii, looking at how our tool path is affected so that we don't build in defects with our tool path is an area that of focus for cold spray. And then thermal management. So most of these stresses are thermally driven. If we simulate it, we see that in simulation and we see that in practice. So the same material, different geometries, we know they have the same amount of stress from peening because we process them at the same conditions. We see some things crack and some don't, and it's primarily thermally driven. So that takes us to the left, where we're working on with collaborators. This work was funded in part by Army Research Lab, looking at simulating the full cold spray process. So here we're taking an actual tool path straight from the warp speed, and we're simulating the particle impact energy. We're simulating using CFD approximations, the heating, convection heating from the nozzle, the convective cooling from the nozzle, convective cooling in the air, still air in the chamber, radiative conduction. So sort of every aspect of thermal energy, how does it get in, how does it get out, and where does it go through this part, and what is the resulting residual stress? And if you look at kind of the bottom left image that's showing the stress, we see stress concentration at the corners, about an inch off the part. And in the previous slide, we saw cracking about an inch off the part. So we're working through validating this. This is experimentally input and experimentally validated in terms of the actual temperatures and the actual heat fluxes. So we're accurate there. And then it comes down to modeling the actual crack process. And what this allows us to do is then go back and say, what green body strength do we need to hit to prevent cracking in this part? Or what do we need to change in the part geometry to prevent cracking? Or, hey, how can we change our process from a thermal standpoint, thermal input, to reduce the gradient, to reduce the propensity for stress buildup? So it's certainly a challenge, just like every other modality. It's something that I think this is a great start to, and that we're working on, and I know others are working on, is certainly an addressable problem, especially with different modalities that are out there and different ways of doing additive cold spray. So the second part is going to be a little bit of a left-hand turn, but the focus I want to look at now is we've discussed where cold spray is good. We've discussed where it fits, where it's kind of challenged, and where we need some improvement. Why should we make that investment? Do we need just another tool belt that can do certain materials, certain sizes, and certain shapes economically? Is that useful? This I hope to kind of illustrate on why the answer to that is a resounding yes. So the real value is in flexibility and advanced solutions. So at the top, these are some sort of high-end advanced applications in fusion, in propulsion, in hypersonics, and I think cold spray has a lot of value here. So the first value statement I think needs brought up is flexibility of cold spray. Cold spray in one system of cold spray can be used additively. It can be used as a coating. It can be used as a repair. There's not many other technologies, and there's really no other AM technology that I would say is as flexible as cold spray. I think the closest thing is maybe powder DED in terms of being able to repair complex parts, clad, and coat. But from the expeditionary standpoint, that's where cold spray really tends to shine. So one system can do a lot of different jobs. So from an investment standpoint, both commercially, but also from the defense industrial base and from the government, if you invest in this one technology, you're getting a lot of return on that investment. It can do a lot of different things. So, you know, $1 goes a lot further for this technology, both as users and as customers. The next part that I think is worth highlighting is hybrid AM. So in our shop, like I mentioned previously, we have a formaloy DED system. We've got a variety of other AM modalities. There's powder bed fusion. There's E-beam and laser in the campus. When we look at cold spray, there's a unique ability to tie it and marry it to other manufacturing methods. In the middle is the Titan Speed system from Speed 3D. And you see it's a cold spray system. It's a large format system, multi-meter capability, but a key facet of it is that there's two pedestals. So you can imagine that other pedestal can have machining on it. It could have a different manufacturing head. It could be a wire head. It could be a DD head is I think what we're really interested in. But it allows cold spray to work with another type of manufacturing method. There's been some really interesting discussions on cold spray in forgings. So can we forge a simple component and then add complexity to it with cold spray? We know from previous slides it can hit the right properties. So can we help kind of buy down the time of a forging by doing the complex operations with cold spray? And can we combine cold spray with the other AM methods? So cold spray and DED, looking at really complex rocket nozzles and rocket engine components. So doing the complexity with things like powder bed fusion or powder DED and doing jacketing with cold spray. It's a technique that is solid state, so we don't have to worry about the interaction as much of what we're spraying with what we're spraying onto. So there's a lot of opportunity for hybrid AM doing multi-material, doing complex materials. Another advantage and selling point for looking at the technology is the ability to process composites readily and out of the gate. So this has been done for years in the traditional cold spray repair side. So wear composites, the whip materials that VRC and Solvis and Pod have developed have been very successfully implemented and fielded. These are commercial. These are used in the defense world right now. Thermal management, and whether that's managing CTE or thermal conductivity or insulation, another really unique place, because from the nature of cold spray that we can spray ceramics or we can spray insulating materials and metals, allows us to kind of go after some really unique applications. Metal composites, again, we're not melting, so we can spray two dissimilar materials, get the properties that we want in a composite, which is not something really feasible in melt-based technologies. ODS materials is a new and I think growing area where cold spray is really going to see some development. We have a NASA sitter along with a few others in the community, and I'm looking at how can these materials be scaled. And when you're using powder bed fusion, you can get some excellent, amazing properties, but you're limited in size and you're limited in scope. Cold spray would allow NASA and allow other stakeholders to scale this to more complex parts in terms of how we apply it, and then in terms of the fact that we could repair those parts and that we could clad other parts. So there's some neat use case there. So the applications for composites, wear materials, erosion, ballistics and armor is a great area. Functional composites, where we're looking at using the properties of the two dissimilar materials. EM and RF management, I think, is going to be a growing place for cold spray additive. Continuing on process, composite processing, reactive metallurgy is a very unique place that cold spray sits and that cold spray can leverage. So if we treat cold spray as sort of a near net shape powder metallurgy process and look at it less through the additive lens and more through the powder metallurgy lens, then you can really do some cool things. So I have 3 examples here of different materials that have been processed where a constituent blend, whether this be master alloy or CP elements or somewhere in between, is sprayed and then is reacted into the final alloy. And so you see an example of NAB, copper nickel, and grade 9 tie or tie 3-2. And we can achieve the comparable cast and wrought properties. So it's a unique way, and this affords us a mechanism of manufacturing alloys that may not be traditionally manufacturable in additive or traditionally manufacturable in cold spray. So I think this is a very unique way that cold spray opens up to process materials. And the final thing that I'll leave the talk with is probably my favorite, and where I think there's a really high ceiling for what we can do, and that's multi-layering and functional grading. I talked previously about the value of cladding. So kind of combine all the other things that cold spray can do, unique alloys, dispersion strengthening, and so forth, and know that you can do that on top of other systems. You can build onto other parts. You can multi-layer. And in the bottom, we show just illustratively the functional grading process. So cold spray can build off of any part in any orientation. We aren't worried about melt pools. We aren't worried about gravity, solidification effects. So we can spray in any direction, and we can control what material is where because we're using powder feeding. So that allows us to control what material goes where on the part and when. So cold spray is really uniquely powder bed, powder DD, the only other capability that allows you to control what material goes where and when, which allows you to do full, true three-dimensional functional grading. And especially with cold spray, we can do this without reacting the materials. So we can functionally grade things that maybe we typically couldn't melt process because we'd form a lot of deleterious phases. We can spray that in cold spray, and we can create some really unique parts for some unique applications. So you could open your mind to something that might need a high temperature on one side and lightweight on the other, or radiation environment on one side, but we want low cost on the other. And how do we get these things to stick together? So with that, I'll thank everyone for their time, and I'll be happy to chat through any questions.
All right. Thank you, Mike, for the very insightful presentation. To start off with some questions, just a reminder to the folks, if you have any questions, please submit them through the Q&A feature on the bottom. So the first question was actually somewhat submitted beforehand. How do you see titanium cold spray evolve over the next 3 to 5 years?
Yeah, that's a good question. I wish I knew the answer to that. So I think there's significant opportunity in cold spray, absolutely. We've sprayed titanium in air, so we don't need an inert environment, and we were able to get reasonable ductility, and that was kind of right off the bat with really no sort of optimization. So you can imagine with optimization, we'll be able to achieve properties in air for titanium alloys. So kind of going from there and knowing that we'll be able to do that, that opens up potentially expeditionary applications, which are not feasible elsewhere. And then just opens up the fact that we can do tie alloys. When we think about the reactive approach, that also opens up new possibilities. So we've talked heavily with powders on demand about this, and that reactive approach can allow for materials that are not traditionally additively manufacturable to be manufacturable. So I think there's significant opportunity. It's just a matter of finding the right application and moving forth on it.
Yeah, thank you, Mike. Another question from our audience is, which of the different additive methodologies do you use most frequently at HAMR, particularly for aerospace applications?
So for aerospace, I would say the cold spray and DED are probably tied. Um, we've had more focus on aerospace for DED. We've had less focus on it for cold spray. We've certainly had aero components come up that we've bid on and that we've teamed on to try to bring forth the ability to process 6061 And there's numerous teams working on 7075. I think we're right around the corner on that. So the ability to process those material lends itself well to aero for cold spray. I think DED is already there for some alloys like scalmalloy and some others. So we use both, probably DED a little more for aero.
Okay, yeah. So you mentioned during the presentation that Cold Spray AM is very close to meeting casting and forging properties. We're a little bit lower on the elongation side, which we could do that through powder optimization as well as process condition optimization. There's an audience that's specifically interested in whether the lack of creep and high temperature fatigue data is also like a major barrier for qualifying co-spray materials for structural applications.
Yeah, it certainly depends on the application, right? So for high temperature aero applications, yes. So there's to my knowledge, there's no creep or fatigue data for cold spray. The way that we're heat treating these, we are certainly going through a lot of grain growth. So we aren't quite as fine grained as what a traditional coating system may be, or repair system. So it's feasible that we could have a reasonable creep strength and creep life, um, but it's completely unknown territory. So I think
Yeah,
that's where some investment really needs to be made.
gotcha. Yeah, definitely application dependent for sure. Another question is on powder distribution and research. How have you found supply limiting your research, and do you foresee an increase in powder manufacturing? Like powder supply limiting your research?
Yeah. Um, it's a good question. I think the biggest limitation is that there's generally plenty of suppliers out there. The two biggest challenges are oftentimes when you're doing R&D, you just need 5 to 10 kgs to check if something works. And 5 to 10 kgs is not something that a powder manufacturer particularly cares to sell. So you can to do sort of early initial work can really be expensive. Um, and the other challenge I would say on the powder side is when we're kind of putting our defense hat on and looking more specifically at those applications, is ensuring that it's a domestic supply all the way through the powder life cycle. So was this material melted domestically? Is this material fabricated, atomized domestically? So depending on what's the alloy that you're interested in, there can be some really severe restrictions. So those are, I would say, the two. There's lots of material available. Only some of it can be used. I
Yeah,
hope that answers
definitely.
that question.
Mhm. And then kind of going along with, like the different materials that we can spray, you mentioned that, high entropy alloys are difficult to spray, especially they have lower DE. Is high entropy refractory alloys, or are you talking about all the high entropy alloys?
So we've only sprayed some, so I can't comment on the entire space. And I think the best way to put it is if you look at what the literature um, says for cold spray, and if we look at ourselves in the vein of treating critical velocity as spall strength, so two schools of thought, if we just kind of commit to that one for a little bit, um, a lot of the high entropy alloys, whether refractory or traditional Cantor alloy, equally the case, have very high spall strengths. So if these equations are true, and if this way of looking at it is correct, then those materials generally are going to have a hard time depositing. We're going to need very high velocities or to change our process to be able to manufacture them. So it's not impossible. We've sprayed them, um, but they're not high DE materials.
Yeah, understood. I have one question kind of along with like the powder types and everything. You mentioned how the cold spray part quality can vary with the different powder type. So in order to qualify the cold spray AM process, do we have to do the qualification procedure for every machine OEM plus powder brand and type combination?
Probably, I think that's agency specific. So I was just having a conversation with somebody from the Army 2 days ago about that exact topic. From the Navy perspective, I think it's relatively locked down to the system to some degree, certainly the feedstock, um, and how you qualify it. I think from like a QSP perspective, and from if it's coming from like more traditional cold spray, and if some of those standards get adopted, it will be a little more open to how are you processing it and what are your process variables. But the challenge that cold spray has is that a pressure for one OEM and a temperature for one OEM are not at all the same as a pressure and temperature for another and for yet another. So since everything is unique, we can't really say with high certainty that one type of equipment processed at the same temperature pressure is really anywhere close to another piece of equipment. Everything comes back to particle velocity. So that's really I think what we'll see as cold spray additive matures is that we're going to have process monitoring be a very critical part of the process. And then that's what's qualified, not the machine, but you're within a certain process window. And that's pretty typical of the other additive modalities, is being in a certain process window.
Okay, we just have one last question, and I believe this will be the last question we can take in the webinar today. So we have an audience asking that there has been relatively low funding in the cold spray area. Do you see this increasing or decreasing in the future?
I hope it increases. uh, no, hopefully this talk has kind of shined some light and some understanding that it's a valuable process to invest in. But realistically, yes, I would say for anyone that's still online, I would highly encourage you to attend CSAT this year and LSAT. I know for certain both we and others will be presenting on some recent developments in cold spray on qualification of cold spray additive. And I think once that's able to be public, once that distribution is released, people will see that this is a viable pathway. You can qualify materials and parts, and hopefully that's kind of the thing that gets the snowball rolling to getting that investment.
Yeah, sounds good. So, all right, thank you everyone for attending. This will be the last question that we're going to answer, and I believe that's all the questions as well. So again, the recording will be provided afterwards. And please look forward to some of the other Action Team webinars next month leading up to our CSAT and LSAT conference from June 9th to 11th. So thank you everyone and have a great afternoon. Bye.
Thanks, Bonnie.